It's a great pleasure to be here at the Airflow Summit again. This is my third time attending and speaking. So yeah, thanks very much for coming along. My name's Nathan Hadfield. I'm a principal data engineer at King. And maybe you don't know us from the company name, but you might know us from we make games. Most famously, Candy Crush Saga, now about to celebrate its 13th year. Still an incredibly successful and popular game. And I think there's around 20,000 levels now in Candy Crush Saga alone. So it's been a huge success for us. But let's take a quick little trip back in time to about a year or so ago at the last Airflow Summit. And I gave a similar kind of talk where I was showing a GPT-powered diagnoser that would hopefully explain why a task might have failed. So today's talk today is kind of a sequel, hopefully a cool sequel like Terminator 2 and not like, I don't know, any of the Matrix sequels. This version that I showed worked, but it kind of relied entirely upon OpenAI APIs. So that meant everything that all the context that we were sending to it was, leaving our infrastructure. Every diagnosis was incurring a token cost, and there wasn't really any flexibility, right? We can only use OpenAI models. But things have changed quite a lot recently. Just a very quick kind of like recap of what I talked about last year. I'm not going to go into too much detail, but just a quick summary. Basically, what we built was essentially like a custom module that hooks into the on-failure callbacks. So whenever your task fails, it hits the on-failure callback, and then we can interact with an AI, and so we would construct a prompt, pull together some context, the exception message, trace back of the error, maybe some DAG code as well, and we'll send that off to the model, and then what we'll get back is like a structured diagnosis, giving us a description of the issue, some root cause analysis, and hopefully some suggested fixes as well. And then that output we can then use, post it out into our task logs, put it into Slack alerts, or put it into things like PagerDuty as well. And what that did is it basically turns every Airflow task failure into an instant AI-powered root cause triage. But it comes with some trade-offs, right? And some of the questions that emerged from this last year were things like this, okay? So, are we okay sending potentially DAG code and trace backs across, leaving our infrastructure to public APIs? What does this really cost at scale? How do we swap in different models or providers? I suppose most interestingly of all, do we even need like a big GPT-powered model to answer these problems? Like, are we just using like a bazooka to kill a bug here, really? And that was this last question that kind of stuck with us, and this is what the rest of this talk is kind of about. Just trying to figure out whether this like compact models that you can self-host might actually, let's say, be a better fit, but might be able to achieve similar results. A year is kind of like a long time in AI, and over the past year, the kind of the LLM landscape is evolving quite a lot. We're seeing not just more models, but smarter models. Models like Quen, Gemma, and such like. They're all capable, and DeepSeek most famously, they're all capable of multi-step reasoning. At the same time, the infrastructure is maturing, right? So it's really easy to run like a 8 billion parameter model on a laptop similar to mine, and tools like Llama and OpenWebUI enable you to run these things with very little setup. And these also expose OpenAI compatible APIs, which kind of makes integrations with these kind of theoretically seamless. And so it's easier than ever to run these models privately. There's a few changes to API logic. We don't have these token costs and vendor lockings, and these things allow staying inside your infrastructure, which might be comforting for some people. Well, I guess it's that kind of shift in capability and control which kind of made this worth revisiting. So what did we kind of do this year? Well, we didn't need to reinvent everything. We kind of reused our callback-based diagnosis framework for this. But in addition to the GPT models, I decided to add in a selection of quite small sub 10 billion parameter models I could run essentially on my laptop here. And because they exposed kind of the OpenAI compatible endpoints, we didn't really have to do much rework, and then use Llama and OpenWebUI to serve these models. I guess we had like a hunch, right, that, as I said, this kind of like problem domain of diagnosing these task failures might actually kind of be well suited to some of these compact models. It doesn't necessarily need GPT level horsepower. And so, yeah, the goal was to, have a fully kind of self-hosted, in this case, kind of locally running privacy-first AI task failure diagnoser, and to then compare the quality of the diagnosis across these different models. Well, so yeah, as I said, we wanted to test these models, and this isn't really to, say what's the best model or generate another LLM leaderboard. This was just really to kind of understand whether these compact self-hosted models can deliver diagnosis that's kind of good enough, right? This is quite a specific area we're focusing on. So it doesn't really translate to broader NLP domains. So what do we test? So we picked a range of models. We've got a couple of the high-performing commercial models, and then a range of compact open source models, ranging from the very small 1.5 billion parameter up to 8 billion parameter here. These are all small enough to run on my MacBook. I say not to really crown a winner, but just to see whether they are viable at least. So then we had to devise a set of challenges, and so we devised 10 scenarios, kind of pulled from real DAGs and pipelines, the kind of failures teams might hit in production. They span a range of styles. Some are structured, SQL syntax errors. Others a bit more ambiguous, API timeouts, rate limiting, and some test kind of pattern recognition as well. And so, yeah, the mix was intentional, just to can they handle not just simple, easy patterns, but ones which might require a bit more reasoning. So we've got the models, we've got a set of problems, but we need a way to quantify how good that diagnosis is. So we developed a little scoring rubric that tried to focus on four things. Identification. Does the model correctly name the issue? Does it back that up with relevant evidence? Can it pinpoint the exact cause, root specificity? And does it give actionable fixes? So hopefully these aren't abstract. They try to reflect maybe what someone coming in to troubleshoot a problem might need, telling them not just what went wrong, but why and maybe what to do next. In addition to this, we want to apply a set of bonuses and penalties to the diagnosis. Basically, try and reward clarity and penalize noise. So models that may be rambling, repeat themselves, hallucinate SQL for non-SQL related failures, maybe drop into languages that we don't want, they get penalized. On the flip side, we want to reward clear, detailed, and well structured explanations up to a point. A smaller model that's concise and on topic, we don't want that to score lower than a larger model which fills space with fluff, right? It's not about verbosity, it's about usefulness. So a good example of a diagnosis given for this fairly straightforward scenario, a good diagnosis might look something like this. It identifies the failure clearly, references error details, offers some actionable next steps, whereas the low scoring example, by contrast, is vague, repetitive, generic guesses, misses the point, and actually kind of hallucinates irrelevant causes. Right, so how did this testing work? So it's a controlled benchmark. We had the same failures, the same prompt, the same rules. So every model saw the exact same failure scenario with the same input context and prompt, and got a single shot at diagnosing it. So yeah, we automated this, of course, through an FO DAG that simulates each failure type, routes it to a model, skewers the output based upon the rubric we just showed. And then those results are calculated and pushed to Bucharoo, where we can do some analysis. And this setup just kind of ensures the consistency, so that when we compare them, we can be sure that the differences are coming from their reasoning and not the environment here. All right, so let's get into some of the results. So how did they score overall, right? So this chart basically gives us like a high-level view of model performance based on average score across all the scenarios. As you might expect, GPT-5 kind of like leads here. But I suppose what's encouraging is this strong middle tier. So like Qwen, Gemma, and Phi, they're kind of clustering in this 60 to 68 range, which is not too dissimilar from what GPT-4o is coming out here. What interesting observation is that model family seems to matter. So these Llama models and DeepSeek variants seem to lag behind the others at similar parameter sizes, maybe suggesting something around maybe the architecture or the training origin play a big role. I'm not sure. And at that bottom end as well, we're seeing like these smallest models, these 1.5, 1 billion models struggling to produce kind of useful output. The averages are not everything. This chart here basically kind of shows variability on the x-axis, right? So the standard deviation and average score on the y-axis, and with some median lines here to break it up into quartiles. And ideally, what you want is a model which is landing in that top left quadrant, high performing and quite stable. And the GPT models are exactly that. But some of the compact models, I think Qwen in this particular example seems to produce pretty strong outputs, albeit with a bit more variability. Phi, Mistral, and Llama are kind of a bit further down, showing kind of higher spread in their performance. But even interestingly, even some of the larger models don't necessarily give you stability, it would seem. And these smaller models are kind of suffering twice, once they're both kind of low score and consistent. I suppose we might, if there's a sweet spot, for these models, we might look at Qwen and Gemma up there as kind of balancing average performance and decent consistency. So just this chart here is basically kind of like focusing on these top 3 compact models and to try and compare them to GPT-5 to see how close they can get. Qwen comes out as the strongest competitor here, sometimes getting close to GPT by about 10 points. The gap grows a bit more in kind of abstract or kind of noisy failures. But I mean, I actually think this is kind of encouraging, actually, because we're using quite small models here, and I would expect that larger models would close some of these gaps quite considerably. But you can see on some of these error types we're getting not too dissimilar from these big models. This chart shows how much model performance fluctuates across repeated runs, so the higher value representing more variability. Again, volatility is more so with the smaller models. Qwen and Gemma on the other hand seem to be relatively stable for their size, but not at GPT levels of consistency. And I suppose what's interesting is it seems that the scenario complexity exposes instability. So these kind of rate limited or schema mismatch problems have higher variability, maybe suggesting something to do with it requiring deeper reasoning or broader context. So what's driving kind of a high scoring diagnosis? Well, GPT-5 leads because it's well-rounded, right? It's leads across all these 4 core areas: identification, evidence, root specificity, and solutions. It's not just verbose. Some of these compact models tend to rely heavily on the kind of identification and evidence. Qwen and Gemma seem to be particularly good at spotting the right failure type and picking up on relevant signals. But when it comes to precision, most of the compact models seem to fall short. Qwen and Gemma seem to come close and seem to come closer in these areas, though. Last bit of data. Where do these compact models lose points? Well, the biggest breakdown is in repetition. It doesn't really affect just the smaller models. Even some of the higher scoring models like German Quena get dinged for being a bit verbose at times and repeating phrases. Maybe that's to do with the prompting. Maybe different prompt strategies might improve that. And we also saw hallucination hitting most models. But in contrast, the GPT models are largely penalty free. And that's kind of what gives them their edge. All right, so let me just wrap this thing up. What's this kind of taught us? How do we interpret this? Well, we're only what we learn using kind of like 10 billion parameter models here. Well, some of these models are good enough, I think, in some scenarios, but clearly, GPT is still winning on depth and stability, but that margin is growing, and even though some of these smaller models are more volatile and prone to hallucinations, we found that models like Quen and Gemma can provide some meaningful value. But what's next? Well, as I said, this only evaluated sub 10 billion parameter models. We're at a point now where hosting much larger models is possible on pretty modest hardware, and I'm fairly convinced that larger models would close some of these gaps to GPTs quite even more. There's just a few kind of caveats about this. I understand that we talk about these self models as being free, and that's true from a token cost and such like. But obviously, there's operational costs in here, and but yeah, this analysis doesn't really tackle those questions. And this is really only focused to like controlled airflow scenarios. This doesn't really generalize to broader NLP reasoning tasks. And I guess finally, I know this is an Airflow summit, and kind of mostly what I've talked about is LLMs here. And from my last talk and this one today, I think I've shown that this sort of thing is possible now. But in this current implementation, this is a custom integration, a custom module that runs in callbacks, right? But I think the good news is that the community is kind of thinking in this direction as well. AIP 91 is proposing a model control plane component where LLMs could potentially assist with natural language debugging. And I think that if we could have the capability for self-hosted models as part of that, as part of this, then we kind of get to the position where having fully self-hosted, privacy conscious diagnosis as part of the core Airflow experience. So hopefully this is not a distraction and kind of a direction. And that's all I have for you. So thank you very much.